The mathematical modeling of financial markets has undergone a profound evolution, moving from the analysis of individual assets in isolation to the comprehensive study of entire systems of interconnected securities. This paradigm shift from univariate to multivariate perspective is not merely an academic exercise in generalization. It is a fundamental necessity driven by the empirical reality of modern finance. Assets do not move in vacuum. The returns are influenced by a complex web of shared macroeconomic factors such as the industry specific news and market wide sentiment, leading to the intricate patterns. Understanding and quantifying this interconnectedness is the central challenge of portfolio management, risk analysis, and derivatives pricing. Multivariate distributions provide the indispensable mathematical framework for this task, offering a language to describe the joint behavior of multiple random variables simultaneously. Univariate analysis, which focuses on the probability distribution of a single random variable, provides a foundational but incomplete picture of financial reality. A univariate distribution can characterize the expected return and volatility risk of an individual stock, but it inherently treats the asset as an independent entity. This assumption starkly contrasts with the observed behavior of financial markets, where assets are grouped into sectors and classes that exhibit strong correlations. For instance, the returns of small cap and large cap equities are often correlated because both are exposed to the same underlying economic fundamentals, such as the GDP growth, inflation, and interest rate policy. Similarly, a shock to the technology sector will likely affect the stocks of most technology companies, regardless of their individual corporate health. The failure to account for these dependencies is most pronounced and catastrophic during the periods of market stress. In a crisis, the carefully constructed diversification of a portfolio can evaporate as correlation coefficients across seemingly disparate asset classes converge towards plus one. Models that assume independence or low correlation dramatically underestimate the potential for systemic risk, leading to devastating losses. The widespread adoption of sophisticated multivariate models in risk management is a discrete response to these historical market failures. A multivariate distribution is formally defined as a function that describes the probabilities for a combination of two or more often dependent random variables. The primary tool for this description is the joint probability density function, which is denoted by F, which specifies the probability density at a particular point in a k-dimensional space. The crucial insight is that a multivariate distribution's primary purpose extends beyond describing the individual characteristics of each variable. Its core function is to characterize the dependence structure among them. While a set of univariate distributions tells us about the expected return and risk of each asset individually, the multivariate distribution adds the critical layer of information about how they move together, their covariances and their correlations. This characterization of dependence is the central object of study in modern portfolio management and enterprise-wide risk analysis. The applications of multivariate distributions penetrate nearly every aspect of quantitative finance. The ability to model correlated systems provides the foundation for some of the field's most important theories and practical tools. Its core importance lies in many aspects like the portfolio theory and asset allocation, and risk management and simulation, and derivatives pricing. The cornerstone of modern portfolio theory is the idea that an asset's contribution to portfolio risk depends not only on its volatility, but also on its covariance with other assets in the portfolio. Financial institutions use multivariate models to understand their aggregate risk exposure. Techniques like the value at risk and stress testing rely on simulating future market scenarios. The valuation of many financial derivatives, particularly exotic options, depends on the joint behavior of multiple underlying assets. For example, a basket option has a payoff that depends on the value of a weighted average of several stocks. In essence, the transition from univariate to multivariate analysis represents a fundamental shift from viewing assets as isolated entities to understanding them as components of a complex interconnected system. Among the vast family of multivariate distributions, the multivariate normal distribution, also known as the multivariate Gaussian distribution, holds a position of paramount importance in quantitative finance. Its prevalence stems from a combination of theoretical elegance, mathematical tractability, and its role as a reasonable first approximation for many financial phenomena, underpinned by the multivariate central limit theory. The multivariate distribution serves as the foundational building block for numerous models in asset allocation, risk management, and derivatives pricing. Now, first, let's look at the definition of a multivariate normal distribution and its parameters. So, a random vector denoted by x is equals to x1, comma, x2, comma, so on till xk is said to have k-variate normal distribution if every linear combination of its components, like y is equals to a1x1 plus a2x2 plus a3x3 plus so on till akxk, has a univariate normal distribution. This powerful definition reveals the inherent stability of the normal distribution under linear operations. The multivariate normal distribution is completely characterized by two parameters, the mean vector u and the covariance matrix. The mean vector is a k-dimensional column vector containing the expected value or mean of each component of a random variable. The covariance matrix is a k into k symmetric semi-definite matrix where the diagonal elements are the variances of each component and the off-diagonal elements are the covariance pairs of the components. The covariance matrix governs the spread, shape, and orientation of the distribution. The variance is sigma I square measures the individual risk of each asset, while the covariance is sigma ij measure how they move together. For a portfolio of n assets, this implies the model is defined by n means and n variances and n into n minus 1 by 2 unique covariances. For the distribution to be non-degenerate, meaning it is not concentrated in a lower dimensional subspace, the covariance matrix must be strictly positive definite. In this case, the multivariate normal distribution has a probability density function given by f of x given mean comma covariance matrix is equals to 1 by root over of 2 pi to the power of k into modulus of covariance matrix into exponential function of minus half into x minus mean transpose into covariance matrix inverse into x minus mean. This formula, while being intimidating, is a natural generalization of the univariate normal PDF. Each component has a clear interpretation. X minus mu is the k-dimensional vector of deviations of a point x from the mean u. The inverse of the covariance matrix is known as the Persician matrix. It reflects the partial correlations between variables. So this whole term is the squared Mahalanobis distance from x to mu. Unlike the simple Euclidean distance, this distance accounts for the variance of each component and the covariance between the components. Modulus of covariance matrix accounts for the determinant of the covariance matrix. This whole term is the normalizing constant that ensures that the total probability over the entire k-dimensional space integrates to 1. The widespread use of multivariate normal distribution in finance is due to its remarkable and mathematical convenient properties. The first one is closure under linear transformation. This generally means that if there is a x which belongs to a multivariate normal distribution and there is a y which is equal to ax plus b, which is an affine transformation where a is a m into k and b is a m into 1 matrix, then y is also multivariate normal with mean of a into mu plus b and covariance of a into sigma into a transpose. This property is of paramount importance in portfolio theory, as a portfolio's return is a linear combination of asset returns. The next property is that any subset of a multivariate normal vector is also multivariate normal. For instance, if we have x is equals to x1, x2, so on till xk, and x is multivariate normal, then the marginal distribution of the first m components out of the k components is also multivariate normal. The conditional distribution of a subset of variables given the values of another subset is also multivariate normal. The next property is that the conditional distribution of a subset of variables given the values of another subset is also multivariate normal. This property is crucial for prediction and for understanding how information about some asset updates our belief about others. The last property is that zero covariance implies independence. For jointly normal random variables, if the covariance between two components is zero, then those two components are statistically independent. Now that we understood the theoretical framework of multivariate normal distribution, let's look into some of its core applications in modern finance. Multivariate normal distribution finds its most significant expression in practical domains of portfolio management and risk analysis. The elegant properties of MVN, particularly its closure under linear combinations and the tractability of its parameters, provide the analytical foundation for some of the most influential theories and widely used tools in quantitative finance. The first one we look into is the modern portfolio theory. Modern portfolio theory, pioneered by Harry Markowitz, revolutionized investment management by shifting the focus from selecting individual assets to constructing diversified portfolios. The theory's central insight is that the risk of a portfolio is determined not by just the individual risk of its constituent assets, but more importantly by their covariances. The multivariate normal distribution is the canonical model for implementing modern portfolio theory. Portfolio's return, RP, is a weighted average of the returns of the individual assets, all denoted by R. This can be expressed as a linear combination W1R1 plus W2R2 plus so on till WNRN, where W is equals to W1, W2, so on If we assume that the vector of asset returns R follows a multivariate normal distribution where R belongs to n of mu comma sigma, then a key property of MVN immediately applies here. Any linear combination of its own components is also normally distributed. Therefore, the portfolio RP will follow a univariate normal distribution. The parameters of this distribution are the expected portfolio return E is equals to WT into E, or transpose of the weights matrix into the expected returns of all the assets, which is equal to WT into mu. And the portfolio variance is a quadratic form involving the weights vector and the covariance matrix. So the portfolio variance is equal to transpose of the weights vector into covariance matrix into the weights vector. So this is the application of multivariate analysis in modern portfolio theory. Now let's look at its application in risk management through understanding the value at risk. Beyond portfolio construction, multivariate distributions are fundamental tools for financial institutions to measure and manage risk across the entire firm. Value at risk is a widely used metric that quantifies the potential loss of a portfolio over a specified time horizon for a given confidence level. For example, one day 99% VAR of $1 million means there is a 1% chance that the portfolio will lose at least 1 million over the next day under normal market conditions. The assumption that the asset returns are multivariate provides a straightforward analytical method for calculating value at risk, often called delta normal or variance covariance method. So the steps of delta normal method are as follows. First, we assume that the underlying risk factors such as the stock returns, interest rate changes, etc. follow a multivariate distribution. Next, we calculate the portfolio's return, RP, just like we calculated in modern portfolio theory, which will be normally distributed with a mean mu p, which is equal to WT into mu, and a standard deviation equal to root over of WT into covariance matrix into W. The value at risk confidence level 1 minus alpha is then calculated directly from the properties of normal distribution. Var of alpha is equals to minus of UP plus sigma p into Z alpha. Here, Z alpha is the alpha quantile of the standard normal distribution. Example, for a 99% confidence level, alpha is equals to 0.01 and Z of 0.01 is approximately equal to minus 2.33. This analytical approach is computationally efficient and easy to implement, making it popular for risk reporting. Its primary weakness, however, is its strong reliance on the normality assumption, which may not hold during periods of market stress, when return distributions often exhibit fat tails. So, in this video, we have traversed the landscape of multivariate distributions, charting a course from their conceptual necessity in finance to their practical implementation in portfolio and risk management. The journey began by establishing the inadequacy of a univariate perspective in a world of interconnected financial assets, where systematic risk and correlation are dominant forces. The multivariate normal distribution was then introduced as the canonical model for capturing this joint behavior, prized by its mathematical tractability and the intuitive power of its parameters, which are the mean vector and the covariance matrix. The practical application of these concepts were understood by looking into the modern portfolio theory and the value at risk model. Despite its foundational role, the multivariate normal distribution is not a pancake. Its assumptions, particularly that of normality, are often violated by real-world financial returns, which are well documented to exhibit properties like skewness and fat tails. These fat tails mean that extreme events occur far more frequently than predicted by a normal distribution, which is a critical deficiency for any risk model. In conclusion, the multivariate normal distribution remains an indispensable cornerstone of quantitative finance. It provides a clear, powerful, and analytically tractable framework for understanding and modeling the correlated nature of financial assets. While its limitations necessitate the use of more sophisticated models for many practical applications, a deep and nuanced understanding of the multivariate normal variable is the essential starting point from which all advanced multivariate financial modeling is built. It provides the language, the tools, and the intuition required to navigate the complex interconnected world of modern finance.